it seems like it's working. All right, let me just message in the Discord to make sure everyone knows that this is happening. All right, seems to be working. All right, what are the current questions for Toddler 2? Let's see how it's going. I know it had a little bit of a slow start, but I think once people get through level 1 and like maybe level 2 as well, that the remaining levels will be pretty, it'll be easier, I think. I think the biggest hurdle will be getting through level 1. Yeah. So I think so the question was basically, should we just copy and paste the functions that Jan wrote in the Q&A? So the functions that he wrote are definitely extremely useful for showing how you can basically abuse both the race condition as well as the heap corruption issue and combine them together to start getting arbitrary reads. And then at the end, he kind of also showed arbitrary writes. I wouldn't completely recommend just like outright copying it. I think to some extent copying it though and kind of looking it over and making sure that you actually understand what it's doing would be a very good idea. I think if you just outright copy it, you'll probably get stuck, and since you just copied the code, you won't understand what's going on, why it's broken. So yeah, I would, if you're feeling very stuck on level 1, hopefully I can address that as well in these office hours. But his code that he has there is very useful, but I would use it as I would make sure that you don't just outright copy it and that you work on understanding it, otherwise you might get stuck, and that's not good. Yeah, like understand, yeah, exactly. So, and maybe what I'll do is actually take his code and just do another like walkthrough of why it works. Maybe that would be the best way to go. Don't know if I have a good way to copy it, but I mean, I can just pull it up in my browser on the side and then just like transfer it over, and then we can go through it. Yeah, I'll actually do that. That seems like a good idea. Okay, so let me start by launching the challenge in testing mode. Actually, 1 second. Someone was trying to call me. Let me just make sure that they know that I can call them for an hour or two. Okay. Yeah. So I don't have the same issue as Jan, where he was like on a laptop without enough stuff going on. The issue for me is that basically I only have one big monitor, and the way that I have everything laid out, I think for Zoom to work, I need to have basically a projected window where it's like kind of always displaying what's live, but as soon as I switch away from that, it's no longer projecting, and then it just won't work. So I haven't had enough time to investigate how to make that work. So yeah, for now, unfortunately, I can't screen share on Zoom. Okay, so let's, actually, don't know if I actually started the challenge. Let me start level 1 in practice. There we go. Okay, so CTF, we'll just make dir toddler2. And I will start by, just to speed things along, since we've already seen Jan go through and write his code for basically getting an arbitrary pointer and his code for getting an arbitrary read using that arbitrary pointer. I am just going to copy from it, and then we will go through and explain basically line by line what's going on there. Okay, so let's start by, let me think of how to copy this. Yeah, we'll just do it this way. Okay. Actually, let me also import pwn. Don't know why he does this insane like OS kill, but for now we will roll with it. I'm pretty sure you can just call os._exit like a sane person. But maybe I am missing something, so we will for now leave it. I see. Almost there. That doesn't look great. There we go. Oops. Okay. And then clean. And then we need to get the arbitrary right. 1 second. Just trying to skip around in this video to just copy it out so we can just work off of the same code and then explain it. Okay. And then, so there is arbitrary read, yeah, okay. Arbitrary read, which takes R1, R2, R3, and the address that you want to read from. And it calls controlled allocation, R1, R2, R3 address. And then we scanf over it. Okay. Oh, not, yeah, so to explain it after. I think that's the end, but let me just double check here. Yeah, and then return link, yep. Okay. So that is what he created during the extended Q&A. So the first thing I'm going to do is let's just run it real quick to make sure that it works, and then I will go through and explain line by line what's going on. Okay, so let's create our process. As process, and then, oops, width. And then we can do, we want our 3 connections. So the exploit that he demoed is working basically with 3 concurrent connections to the program. So we can do, let's go ahead and say R1 equals pwn.remote localhost, 1337. We want 3 of these. Oops. Okay, and it looks like this will already clean them for us. And then we just want to do an arbitrary read, I guess. R1, R2, R3. We need to figure out actually where we want to read from. So in level 1, how do I show this? Let's show we launch toddler 2 and then we netcat localhost 1337. Actually, I guess it told us in the, oh, I'm in testing. In the teaching one, it'll tell you basically that the secret is stored in the BSS. So basically the way it works is that we want to have ultimately call this send flag function because this will give us the flag, but it asks us for the secret before it will actually give it to us. And if we give it the wrong one, it says not authorized. If we give it the right one, it'll say we're authorized and print out the flag to us. We have the ability to do this malloc, this free, this scanf, and this printf, which I will get further in a little bit here for explaining exactly what's going on. Okay, so Let me close that. Close that. Okay, so the question, or the first thing that we need to figure out is where in the BSS we're storing it to. So actually something else to note is that with level 1, what? Oh, that's right. Check sec for some reason makes that impossible. Okay, so something to note for level 1 and level 1 only is that PIE is disabled. And since we're storing it in the BSS, it's just going to be at basically a constant address. We don't have to really leak something and then do an offset of that leak or something like that. It's just always going to be where it's going to be. And we need to figure out where that is. So if we go ahead and do this, and then we want to jump to main because that's where it's going to ultimately load it up. Actually, I know for a fact it's going to call load secret at some point. Okay, and it tells us here that secret is at this address here. So this is where the secret is going to be stored. There's going to be 16 bytes of secret. As it turns out, our leak only allows us to leak 8 bytes at a time, but you could either, turns out you can actually leak it backwards and that would work, or that you can just kind of go through and run it all twice at the 2 different offsets, since the secret doesn't change. It's kind of constant for whatever your flag is. Okay, so let's go back then and go into Emacs. Let's go ahead and just say secret adder equals that. Okay, and that's exactly what we want to leak. So for now, let's just leak the first 8 bytes, and then we can look into leaking more if this works. Okay, so in theory, if I copied everything straight out of his code, this will actually just immediately tell us the secret. Or you might have to run it a few times because of the race condition, but we will talk about that more. Oh, and we'll also have to import some things. I think it's probably actually just OS. Okay. Okay. Reference before assignment. Okay. Actually, I forgot to see what line that was. That was on line 42. Okay, let's just go ahead and do global IDX. Actually, do we have it set up to be printing things? Did I skip over that part? Let me see, 1 second. Oops. Whatever, we'll just add it in ourselves. Okay, so let's go ahead and once we're out of this loop, let's just print allocation loop done or something, just to tell us we're making progress in our exploit. And then let's also just print what we're trying to point allocation at. Pointing allocation at hex address. Okay. And then let's run that. Allocation loop done. Oh, we're not like printing anything, are we? But why would it not exit? Hold on, let's see here. So there's definitely no loops that are gonna happen after this, but I guess we could be getting hung on something. Let's just call this leak and say print leak leak. And I think this is going to return an integer to us. So for now, let's just call hex on it. And yeah, let's see Actually, is this message? Yeah, I think that's right. Okay, let's see. So we're getting stuck on something. So we're getting stuck maybe on this read until message colon blah. Okay. So we sent this. Okay, hold on. Let me see something real quick. Okay. Let's see what is coming back. I'm just quickly looking to see if anything doesn't make sense. Actually, you know what? Yawn at some point I remember swapped this. Let's just go with that. Let me see what it was that he swapped. I remember he split that apart to happen from two different things. Let me see if I can find that. Hold on. Or let's just YOLO it. Let's see if this works. I think this is what he did. Okay. Okay, so we're still getting stuck. Let me turn... Actually, that'll be hard to do there. Well, I guess we could do it after this loop. So after this loop, we can do... wait a second. If we're getting through this loop, where are we getting stuck on? Hold on. We'll do it anyways. Context log level equals debug, which will make pwn.tools basically just start reporting everything going on to us. Okay. So we sent this, we sent this. Okay. And then so we called the mount, called the free, we called send line of the address. Oh, but we never called like a printf or something. There's no way this logic makes sense. Did I like copy from his code wrong? Hold on, let me see what's missing there. So the issue is that we're calling scanf, but we're never calling printf, and it's printf that actually tells us like message colon whatever. Hold on. Okay, I think I was starting to copy his arbitrary right. This makes way more sense. Yeah, this logic doesn't make any sense. So as you can see, like we're already like trying to overwrite data, right? But in theory, based off of the name of this, certainly, right? We've already controlled our allocation to give us basically, to have basically malloc already at this address. We can see at the very last thing we do is call malloc here. So in theory, this should already be pointing at address. So this scanf doesn't really make sense. So if we do instead printf, and like sending data there, this is like getting ready to do an arbitrary write. So let's see if this works. Yeah, this like sounds way more sane. And that does not work because we seem to have forgotten an F. Yeah, we don't want a B, we want an F. Oh, we can already see though in our history that it was working. Okay. So in this case it failed. Realistically, the sane option would be to like see if it failed and just kind of rerun it if it failed. And maybe I'll add in support for that rather than just like having to rerun it yourself. Because we can already detect like, hey, we didn't leak it correctly, so something went wrong. Okay, and here we can see, it's more readable actually in this debug message that we are able to do a leak. Okay, so as I said before though, it's not really all that exciting to just go through and copy Jan's code and just like go from there or something. That's kind of lame. And maybe more importantly, like you're probably not going to learn just outright copying it, and you very likely could get stuck because you don't understand what this copied code is doing. It's no good. The whole point of this class is to learn. Let's not just copy code. Okay, so what is going on in all of this code? So maybe it would make more sense if I start by kind of describing what our problem is. And you would discover this doing reversing, but for brevity's sake, let me just kind of tell you what's going on. It's basically the same thing as what Jan showed in his Q&A in terms of how this challenge problem is set up. So if let's just create something, we'll just call it challenge or whatever, who cares? Okay, so how does the challenge work? So we have a few operations. Trying to think, how can I easily show? Whatever, we'll just write out what they are. So we know we have the ability to do malloc. We know we have the ability to do free. We have printf, we have scanf, and we have send flag. These are our operations that we get to do. So the way that they work, you've already seen kind of in baby heap, maybe kind of how this works to some extent, is that we're specifying an index when we call malloc. We'll also note that unlike baby heap, we're not specifying a size. We don't get to specify how big of a thing that we're going to malloc, but turns out for our purposes in exploiting, that doesn't really matter. All that matters is that it's small enough and it's going to end up in Tcache. We don't care about controlling the size per se. We just want to corrupt it into allowing us to malloc basically to an arbitrary address. Okay, so how does this work? We have basically 16 allocations just sitting in global data accessible to all threads. We also have basically 16 booleans like is allocated or something. That's kind of how you could think about that. So how malloc is going to work is it's going to check first to see are we already allocated. So like it'll be, I'm just going to write it in like Python-ish pseudocode. So if not is allocated, then we will just call like malloc 1024, and we're going to do like allocations index equals that. Actually, and then also we have to specify index. So this is the basic gist of the logic for how malloc works. It checks to see if, and we can basically assume that all of these start out to like false, 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 whatever. Or maybe we'll stick to Python-ish notation, whatever, good enough. And maybe these just start out as like null, 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 blah, blah, blah. Okay, so this is how it's all initialized too. Because it's in the BSS, which basically means it's going to be 0 initialized, and these are all like the 0 values for their types. Okay, so what does malloc do? Malloc checks, are we already allocated? And if we're already allocated, we don't want to call malloc, because if we did that, then it would be like a memory leak, right? We would have malloced over something where we already, so like right here would be, say it's like the second thing. This might be like 1, 2, 3, 4 as what malloc returned or whatever, and this would be like true. We wouldn't want to allocate again, because then we would overwrite this 1, 2, 3, 4, and it would become like 1, 2, 5, 6, but that pointer to 1, 2, 3, 4 would have just suddenly vanished. We'd no longer have like a reference to it and be a memory leak. So that's kind of like conceptually why a program might want to do this. We want to like basically keep track of what's allocated and not have memory leaks, basically. Okay, so we'll just go back to null, null, null. So this is kind of maybe a fairly common pattern, that if you have a bunch of allocations and you want to like start maybe randomly storing data of the users in it, but I don't know, you could kind of think of how a program might be written in this way. Okay, so what does free do? It does kind of the opposite check. It checks if something is allocated. So if is allocated index, and then if it is allocated, it'll call free allocations index. Okay, this makes sense because we don't want to call free on like null or something that isn't allocated. We only want to free it if it is. Oh, and actually something to point out here, I guess I missed it, is that is allocated index now equals true, and is allocated index equals false. So it's basically just like a single bit state of this allocation, basically checking is it allocated or is it freed right now, and only allowing us to do kind of the opposite operation. And then also these, we only want to do them if something's allocated. So we'll say like if is allocated, actually is that what this is doing? I'm pretty sure we would do that, but maybe we don't check that. Hold on, let me cheat and look at the program. Maybe we don't do that. Maybe this is yet again another bug that we introduce into the challenge. Oh no, we do that. Right. That's what causes it to say like message none. And yeah, okay, so this is what happens here. But we don't exactly check. This is what we do though. So I guess we can keep it in this notation. So if it is allocated, what we're going to do is we're going to printf message and then like allocations index, right? So whatever the data is that's stored in this program, we'll just kind of print it out. And then otherwise, we'll just print, we'll printf message none or whatever. So that's kind of the logic of printf. And scanf is similar. So something else to pay attention to is on the stack, there's like an input buffer. And the input buffer is basically when you type in malloc, we're calling scanf to this input buffer, and then we compare to see if the input buffer is malloc or if it's free or whatever it is. So that actually also exists. It's not super relevant, but it's kind of relevant in the case of scanf's logic, which does if is allocated index, we will go ahead and call scanf to allocations index. So this allows you to like basically put data over that allocation. And otherwise, it turns out we actually just call scanf on input buffer. But this doesn't really matter. There's not really an exploit here per se. At least I don't think there is. Either way, it doesn't really matter for our purposes. Does anyone have any questions over how this program is working in terms of just like the challenge program itself? it's kind of important to understand how the challenge works before you start exploiting it. And then of course this basically like ask for secret, if secret correct, print out flag. And I guess something different than the heap challenges, you can't actually overwrite the secret and make that be like your attack plan. When we go to check if the secret is correct, we basically regenerate the secret on the fly and compare with that. So even though we're storing the secret in the BSS, we're not actually comparing with that. We're just like generously leaking the secret into the BSS. Overwriting, it's not going to allow you to win. You have to read it. Just kind of something to point out. It's not too big of a deal. You might have gotten stuck on that, so it's important to know that. But the exploit's basically going to look the same for most purposes. Okay, so this is the logic. I don't see anyone asking any questions about how the challenge works, so I'm going to assume that it kind of makes sense. It's pretty similar to baby heap with maybe some minor differences. Basically the main difference being this is allocated, that we're maintaining whether or not we've allocated. So if we were to just do this single threaded and try and exploit this, we wouldn't be able to do like malloc. So we would be able to call malloc, and then we would be able to call free, but then we wouldn't be able to do scanf over this freed buffer because it checks if we're allocated in order to allow us to actually overwrite this now freed data. It would actually just scanf into the input buffer, and this is where basically most of the baby heap levels, the logic behind why that exploit works would no longer work because we actually track if something is allocated. However, this is not, yeah, there's a question, go for it. Yeah, the challenge we'll just call malloc 1024. I think it's 1024. I'm not 100% sure on that. I think the input buffer here is 1024 also. Oops. And I think all of these like scanf %s's are like %1024s. So I don't know. It's just specific to the challenge. It doesn't really matter, except that this means it's going to go into Tcache. That's like right on the threshold that it's still able to go into Tcache. If you went a little bit bigger, it would no longer go to Tcache and things would get probably more difficult. But yeah, it just happens to call 1024. So unlike the heap challenges, you don't specify the size, but that doesn't actually matter for just trying to get an arbitrary read, arbitrary write. It doesn't really matter that it's a 1024. Okay, any other questions on, oh, okay, so there's a question in Twitch chat. So the racing Jan talked about in the last lecture has to do with racing the if statements, correct? Exactly. So whereas in baby heap, we don't have these is allocated checks, and we just kind of make it more vulnerable or whatever. But it's single threaded, so that's kind of makes sense why you need that. This is now multi-threaded, but does have the checks. So in just using one thread, one connection to the program, you're not actually going to be able to exploit this. But using two connections to the program, since these allocations and is allocated are just global data shared across all the threads, whereas something like this input buffer, for instance, is living on the thread stack, so it's kind of like specific to each thread. Not that that really matters, but something to kind of note. The way that you exploit this is doing both a heap metadata corruption, basically corrupting the forward pointer. And in order to do that, you need to race it. So the way that you would race it, if we think about kind of what we're going for. So what we really want to do is we want to scanf over, so we want to scanf some freed allocation. Right, this is how we do it in baby heap. So this is our, let's say, our exploit logic at a high level. Is what we really want to do is we want to call scanf on some freed allocation. Because it's freed, it's now sitting in Tcache. So if we think about some freed allocation, the way that Tcache is currently going to look, if we have, let's say, some freed allocation, Tcache is going to be a linked list where we have some freed allocation pointing to, let's just say first 8 bytes inside some freed allocation, right? Freed allocation. This is how the linked list structure of Tcache works, right? We just kind of store the next pointer, the forward pointer, as the first 8 bytes inside of our freed allocation. So if we were to go on to call malloc, it would give us, let's call, we would get this, and then Tcache would be updated to be this, and then if we called malloc again, we would get this. And of course, if we're able to call scanf on some freed allocation, basically we are controlling the first 8 bytes, or however many, but more importantly the first 8 bytes, which means that we are controlling the result of second malloc. And as we said, this is allocated check prevents us from doing that all in just one thread, because if it's no longer allocated, as in basically if it's in the Tcache already and we're like able to track that, then we're not actually going to call scanf on our freed allocation. We're just going to call scanf on the input buffer, and you can basically think of that as just kind of discarding your input. Okay, so in order for our exploit logic to work, let's see how this looks. It's good enough. Okay. We'll just kind of go crazy here. Yeah, good enough. Okay, so in order for our exploit logic to work, we need to abuse the fact that we're multi-threaded and operating on this global data, and we're operating on this global data without semaphores, which is kind of the solution to race conditions. But the thing to note is that semaphores kind of require the programmer to introduce these semaphores. It's not something that we can just introduce generic security mitigations to fix. If you don't use semaphores, you don't use semaphores, or if you use them incorrectly, use them incorrectly. There's not like, we can't just like introduce like ASLR and that just like makes the exploit a lot harder or whatever, like these generic mitigations. Yeah. So, I mean, I guess there is a generic mitigation actually coming up that's in actually the latest libc that breaks kind of how this this forward pointer logic works, but we're going to say we're on Ubuntu 20.04 and we're just going to use their libc, and Ubuntu 20.04 is the latest long-term release of Ubuntu, and good enough. It's still a very valid target. Okay, so anyways, getting back to translating our exploit logic maybe a little bit deeper into how it needs to work. So the way that this exploit logic needs to work is that we need to interleave these malloc free and send flat, and this scanf operation to some extent. So what we want to do, if we just copy malloc and free, and let's just say that this is thread 1 and this is thread 2. So let's just assume we have one thread calling malloc and one thread calling free. So and then we have our global data, which is like is allocated. For now, let's just say we're working on, like index equals 0 for both of them. We'll just say that. Okay, let's say initially it is set to false. Okay, so how do we interleave these operations? Or more importantly, I guess, is it possible to interleave these operations in a way that it breaks the thing that's securing the program? That's kind of what we want to think about in terms of these timelines. So we'll just think about it at interleaving these operations at these super high levels. In terms of like, let's just pretend that free is atomic. It's just like one operation that's bundled together. That is not actually the case. In theory, you could be racing partway into free, because basically every instruction that free has to call, and free might call hundreds of instructions, you might be able to interleave somewhere in there where the race condition is. But let's just pretend free is just this atomic operation, and that all of these 3 lines are basically atomic operations, even though that's not exactly true. Maybe the first step is to see even if this high-level logic can be erased without having to worry about, like, at an instruction level if it can be erased. Okay, so is there some sequence? So I guess the way you might think about this is, let's just assume that we have our thread 1 and our thread 2, and they are executing. Is there some sequence of, like, let's pretend that we get to control which thread we want to step next. So let's pretend only one thread is going to step at a time, and we get to choose which one. Maybe that's how you can think about race conditions in order to see if there is a race condition. So we know that at some point, okay, so the way race conditions work is that it is going to be some interleaving of instructions that results in some bad state of the program, or maybe something that may have some security issue related with it. So we know, for instance, that these is allocated checks that we're doing all over the place are kind of there, maybe in some sense, as a security mitigation, that we're trying to make our program be secure. But due to race conditions, due to the fact that we're not just executing sequentially in a single thread, but that we might get to execute sequentially in multiple threads, you could think of it in some sense in order to, if you want to check to see if there's a race condition, construct the 2 threads like on paper or whatever, or like in Emacs as I'm doing here, and see if there's a way that you can just step through these instructions in a way that violates the security of the program, in a way that gets you into a state that you want. So obviously the CPU is going to execute it as the CPU does, but due to context switches happening, basically context switches happening, or maybe one CPU core running faster or something, these operations can start to be interleaved in various ways. It's not guaranteed, for instance, that in thread 1 we're just going to execute this, and then in thread 2 we're going to execute this, and then we're going to go back to thread 1 and execute this, and then we're going to go back to thread 2 and execute this, back to thread 1 and execute the next one. We're not just going to like alternate between these operations, for instance. We might execute all 3 of these and then execute all 3 of those. We might execute like 2 of them and then execute like 1, and then execute like this, and then execute like 2 more. Like, there's all sorts of options that the CPU might go in. And for now, let's just say that a particular thread will be sequential, but the intermixing of this, and you have to think that this is operating now on global data that is shared across all of the threads, that we can have impacts on the global data and put the global data into a state that the programmer did not intend for. Okay, so what we want ultimately, or ideally, I guess I would say, is for us to have a freed allocation. So let's just think back actually to our XSplit logic. What we really want to be able to do is call scanf on some freed allocation. But the thing preventing us from doing that is this is allocated Boolean, right? We want basically for some allocation to actually be freed, but for the program to say that is allocated equals true. So if we can make it so that, so let's maybe say like goal, have a freed allocation 0. Let's say like we're just working on allocation index 0, index 0, but is allocated 0 equals true. Like this would be great, because this would mean that we could do a scanf over a freed allocation. This is exactly what we want for corrupting the metadata. So there's a question in chat in Twitch chat, what challenge are we discussing? We're kind of discussing in some sense the current 6 levels that are out, and I guess also what will be the 7th and 8th level as well, and then eventually it'll switch over into a different direction. We're just kind of discussing, again, at a high level view of how the challenge works and what security properties we are abusing. Yeah, okay. So our goal, as I said, is to have a freed allocation index 0, but is allocated 0 equals true. So if we look at this program sequentially, it seems pretty likely that the programmer doesn't expect this state to be possible, right? If we free something, the whole idea is that once we free something, that we set is allocated index equal to false, right? This is what we're doing. This is the whole idea. Okay, so how can we abuse this then? Let's see here. So we may actually need to have our initial state. So we're kind of assuming, let me move this after the goal. We're kind of assuming that this is our initial state. But we can obviously potentially mess around with it. Like we could start where we're in a situation where is allocated index is equal to true, for instance. But let's see if we can do it with this. So in order to get this state up here that we're talking about, basically something be freed, we would need this operation to occur, and then this operation to occur, and then this operation to occur. Yeah, and we need that order specifically. We actually can't allow this to happen before, because then we would have called free, set it to be false, but then we would malloc it, and we would get that same allocation back, which means it would no longer be a freed allocation, and we need it to be a freed allocation. So this operation, we can't actually go like this, and then this, and then this, and then this. What we want to have happen is we want this, so that our allocation gets freed. We're forced to set is allocated index equal to false. But then if the thread was hanging right here, and we get to resume execution here, we could set is allocated index equal to true, which would result in exactly what we want. Once we have this situation, it's a win. So maybe we'll want to write the sequence of events that we want. So we want this, and then we want this. Oops. Yeah, and this is allocated buffer is, of course, as we keep saying, is our, what am I saying? Is global data, so it's kind of shared across all threads. Yeah, okay, so this is the sequence of events we want to have happen. So let's see here. So we can't, ideally what we need then to have happen is that at some point we need to get thread 1 to stall out after it executes this, and then for us to go back into this thread and execute. Okay, so if is allocated index is false, we can, so if we're thinking about it, right, thread 2 needs to get into this. So is allocated needs to be set to true at some point in order for us to get into this basic block here. And we're assuming that is allocated is initialized to false. As we said, we could actually configure the program in a way where that's not true, but we can see here in thread 1, we would be able to enter this block. So both of them at some point need to enter their blocks. Let's see here. So this might be not possible given 2 threads. We might need a 3rd thread doing stuff. Let's see here. So in theory, we have it set to false initially, so we can enter this block. But then if we were going to go and execute this to make it true so that we could actually enter into this block, we would have already executed this statement. And we need to stall out on executing this statement until after these two things have happened. So we can enter this block, execute these two things, but we can't just stall out here and not execute this yet. We need to also execute this in order to enter this. So that's basically our race condition here in this configuration isn't going to work. Okay, let's consider maybe the opposite case if this was initialized to true. In this case, we can immediately enter here, but then we can't enter here because we would have to execute this and this, right? We would have to specifically execute this before we could enter this block and execute these two things, which means we would execute this after we executed this and this, which is, again, not an order that we want. So we can already see that given just these two threads, kind of thinking about this at a high level of how we want our race to play out, and we want the race to play out in exactly this way. Again, remember, we can't have malloc be called in between here. That's not what we want. We can see that just given two threads and maybe initializing this to either true or false isn't enough for us to make this race condition happen. Okay, so we're able to have an arbitrary number of threads. What can we do then? Let's see here. So in my mind right now, I'm thinking like, what if we have some thread over on the side, a third thread, basically just constantly calling malloc and free. And actually, we can kind of guide our solution to thinking about this high-level problem. If we look at what Jan's solution was, because of course Jan's solution is going to be implementing exactly what I'm talking about at this high level. So we can see that in this loop he has R3 calling malloc, this guy calling scanf, this guy calling free. So he doesn't actually have, you kind of think of it as we have one thread calling malloc, one thread calling free, but then the third one is just calling scanf. Interesting. Oh, interesting. Okay, so what I was discussing before, in terms of how we wanted to do it. So before I was saying basically that we want this line to execute, then this line to execute, and then this line to execute, right? This was kind of the high-level overview of what we wanted the execution interleaving to look like. And that we couldn't have this happen, right? We just needed this, then this, oops, and then this. And that we couldn't have this happen in between. But there's actually a way that we can be fine with this happening in between. And the way that we can do that is if we have some third thread just calling our scanf logic. So if we do, let's just copy this as well. There is a way that we are fine with it calling malloc. And the way that we are fine with it calling malloc, that we are fine with it calling malloc, is if malloc happens after the scanf goes through. So really what we're trying to do, right, is eventually call this scanf to overwrite the forward pointer so that the T-cache will be updated with, will basically have corrupted the forward pointer and be able to hijack it. Yeah, okay. So let's look then at how can we do it with these three threads, given these three operations happening. And I think it's really worth it with race conditions to just like conceptually think about how many threads are at play, what operations are they doing, how do we need stuff interleaved. This is like kind of how you can get race conditions to kind of click in your mind. And this is the tricky thing, is like a developer writing a program and using semaphores and stuff and trying to make things efficient because there's some overhead introduced by using semaphores, so you don't want to like use them non-stop all over the place because you could basically end up making your program just like effectively single-threaded if you just go crazy with semaphores. As like the developer writing this program, you have to actually be thinking through these sequences of events that can carry out, and make sure that your semaphores are set up in a way that doesn't cause a bad sequence of events. So as a security person going after it, we're kind of doing the opposite, right? We're doing the same thing, right? We're just interleaving events and seeing if we can get a bad sequence of events to interleave. Okay, so given that, so we figured out we couldn't really do it with 3 threads. We kind of proved it to ourselves that given all of the constraints. Yep, there's a question. Go for it. Okay, so the reason we couldn't do it with 2 threads is that in the case where is allocated is pre-initialized to true, how can we execute, right? So at some point we need these 3 things to happen in this order, right? And I keep saying that not malloc here for 2 threads. And the reason I keep saying not malloc here is that if we called malloc here, we would no longer have a freed chunk, right? Does that make sense? That if we called malloc here, we would basically free our allocation, and then we would malloc and get that exact same allocation back that we just freed, which means we wouldn't have a freed allocation set where is allocated is true. Does that make sense? Okay, so yeah, so we can't call malloc here. And the reason then that we can't do it with 2 threads is that if this is initialized to true, we can enter this, and to make these things happen, we need to basically enter both of these blocks at some point. We need to pass the is allocated versus is not allocated checks in order to execute the code inside. So when it's initially true, we can enter this block, so maybe thread 2 steps forward, executes freed, and then we can execute is allocated. And now thread 1 is able to enter because we just set is allocated to false, which means thread 1 could theoretically enter here if we decided to resume execution on thread 1, but we're going to call malloc and it's an issue. And that's the only way we can do it. And then if you set it to false, the opposite is true, basically. If we initialize to false, we're allowed to step here. We can't step here because if we stepped here, we would basically no longer be executing these 2 things. So we would step here, we would malloc, we would set is allocated to true, and now thread 2 would be able to step in order to actually execute this code, but it would go in the wrong sequence of events. So 2 threads just doesn't work for us. Okay, so, but we can do it with 3 threads. And the way that we do it with 3 threads is that we're actually fine with malloc executing, as long as this scanf gets its logic in the right order. So let's look at a sequence of events across all 3 threads where we're perfectly fine with what's going on. And I'm not entirely sure off the top of my head whether we want this to be initialized to true or false. I'm going to guess false, but it might need to be true. But either way, let's try and see if we can step through in a way that abuses this program. And the way, actually, let's go back. The way that we can now abuse this is, as I keep saying, we're now fine with thread 1 calling malloc here, in theory. And we'll say that this is thread 1. Maybe we'll add some spaces, make it look cool. This sequence of events, but this isn't quite enough. What needs to happen in between these 2 things now? Oh, I guess this is interesting. Okay, so what we need to have happen here is that we need to pass this check. Well, maybe we won't specifically say that for now. What we want to have happen though in between here is this right here in our 3rd thread. Our 3rd thread needs to call scanf, and if we call this scanf before the malloc happens, now we've corrupted the forward pointer in here, and we've made it so that after this malloc goes through, the tcache header pointer is actually going to be pointing to whatever we just scanf'd in. So if we can sneak this operation in between, we're fine with this malloc going through. Does this make sense to everyone? This is like critical to understand that this sequence of events results in a corrupted forward pointer where now we basically control where malloc is going to send, what address malloc is going to return. This is like critical. This is the crux of everything, basically. That these 5 events happen in this order is what allows us to corrupt heap metadata, control the forward pointer, and now have an allocation wherever we want it to be. And once we have an allocation wherever we want it to be, we can either printf from that, which means we get to leak arbitrary data, or scanf, which means we get to overwrite arbitrary data. These 5 events happening in this order is exactly what allows us to abuse this program. Hopefully that makes sense. So is this possible? Does that make sense? Sorry, what was the question? So I'm not even necessarily saying, is this possible? We have to now figure out, is this sequence of events possible? But do you at least agree that if we were able to execute these calls in this order, that we would corrupt the forward pointer with arbitrary, basically we would get an arbitrary forward pointer, which means an arbitrary allocation. Does that make sense? So again, I'm not even asking if this is possible. So maybe this isn't even possible. But do you agree that if these 5 operations occurred, and we can even maybe like temporarily ignore these 2 things, right? If these 3 operations occurred, do you agree now, right, that when we call free, we have a allocation sitting in the T cache. We call scanf over that allocation sitting in T cache. We basically get to overwrite the first 8 bytes of it. And then malloc goes through. Malloc basically reallocates this allocation that was freed, but now the head of T cache is pointing with those 8 bytes that we set up. Does that make sense? Right? This is exactly what we explore in baby heap. Okay, so that is, if we can cause that sequence of events to work, we will win. So let's see if we can do that. Is there a way that we can step these 3 threads forward given whatever initial configuration of is allocated? We can probably make this be either true or false, setting it up. Let's assume it's false because that's the initial state of the program. Okay, can we step this forward then? So we need to, so is allocated, so we can't step here because is allocated is currently false. That's fine, but this guy in theory can step forward. I'm thinking that we don't want to be initialized to false just looking at this. Okay, so let's assume it's true instead. So let's say something was already malloced for this index. Maybe we just set it up, made it be true by calling malloc at the start, which basically initializes to true, and we already have something malloced or whatever. That's fine. So if this is already true, what can we do? We can step forward in this thread to basically enter the basic block that we wanted to enter. So we're able to be executing here in thread 2 now. We can step forward here, and this is now executing in thread 3 because we basically is allocated is true, so we're able to walk through both of these. Okay, so now how do we want to execute? So we want to execute, as we said, we want free to execute, and then this, and then this, okay? And we're already set up right now to where all 3 of these operations can execute, right? So, and maybe even more simply, let me actually back this up and let's start back at the initial configuration. Yep, okay. So other thing to note, even though we're saying basically in order to figure out if a race condition is possible, ideally we're not doing like a single instruction and then going to the next thread and doing a single instruction because the CPU is probably not going to let that happen. We can probably context switch. It's theoretically, maybe it's possible, but it's the more times you rely on your threads context switching around, the less likely it is. Oops. So let's see if we can get this in a very efficient order of execution. That's not super critical for it actually technically being possible. But let's just walk through, ideally with as few switches between the threads as possible. So let's say we go through, we execute on thread 3. We're just going to switch over to this. And that like returns true or whatever, so we're fine to continue executing. Actually, hold on, that's not what we wanted to execute first. We wanted to execute thread 2 first. We want to, all right, let's ignore this efficiency idea for a second here. So in thread 2, we execute this, and then we execute in thread 2 our free condition, so free allocations index. So now these two operations have executed in thread 2, which means this is pointing here. Actually, hold on, my headphones are starting to die. Let me just move one of them. Hopefully that's good enough. Hold on, let me make sure it's not completely dead. Yeah, it seems fine. Okay. So we just executed these two operations, and then let's say we context switch into thread 3 executing, and we execute this operation in thread 3, and that's going to return true because we haven't changed the value of this variable yet. So that returns true. And then we execute, let's say, then let's say we execute our scanf in thread 3. Scanf executes. So we did our free, we did our scanf. Okay, and then thread 2 goes back and executes now and sets this to be false. So thread 2 executes. This gets set to false. Okay, so now if we update everything that's executed, we've executed everything that needs to happen inside of thread 2. We've executed everything that needs to happen inside of thread 3. And now let's say thread 1 resumes. And when the thread 1 resumes, it now does its check. And this returns, I guess we'll say it not is allocated returns true. So we're able to enter into this block. And then we execute these two things. No problem. Okay. So through this sequence of events, which is totally possible, if we interleave, we can kind of think that basically we executed free, and then, or maybe like we pass this check in thread 2, we pass this check in thread 3, and then thread 2 does its free, then thread 3 does its scanf, and then we decide to make this now be false, and now thread 1 is able to theoretically pass through this and do its malloc. So what we just did, we can see, and I guess maybe we don't completely care about this because we didn't exactly get this sequence of operations. We can see that this is kind of out of place, but that's fine. Ultimately, what we really care about is the sequence of free, scanf, and malloc. Yeah, okay. So if we just kind of strip away all of the maybe unnecessary stuff, and we just show that this is possible, we got this sequence of events, right? And this is exactly what we wanted in order to corrupt the forward pointer. So this shows that it's possible. Okay, so now let's look at what Jan wrote yesterday or Wednesday during the extended Q&A. This maybe will start to now make a lot more sense. Okay, so what did he do? So he called malloc and then free, which theoretically would initialize this to be false, which isn't actually what we want. But in theory, this is executing out of order because this is going to two separate threads. So I'm not exactly sure what's going on here. Let's kind of ignore it for a second. Let's just pretend that this guy stalls out, this free operation. I don't fully understand this. Oh no, but that's not an issue. Okay, the reason that's not an issue, so let's say that is allocated is still false after this. We do a malloc, we do a free. For some reason, he's setting this up such that thread 3 basically gives us our malloc, and then we decide to introduce that into thread 1's Tcache. But that's fine. That doesn't really matter. The more important thing, though, is that we can see that we have this while loop. And whenever you see like a while loop in this racing sort of situation, like we're basically just trying to get a bunch of threads executing as fast as they can, doing a bunch of operations until eventually we interleave in exactly this way. Or maybe an equivalent way that is just as bad. Okay, so we call malloc, which would initialize us, if we assume that this succeeds, this is, yeah, exactly, this makes sense. Okay, so we call malloc right away, and we clean, which kind of means we're like gonna wait a little bit, which means this is going to happen, like guaranteed, basically, in this order. Like malloc is going to have happened. So now is allocated is set to true, which is what our attack relied on. Our conceptual attack relied on is allocated being set to true. Let me switch out my headphones since I don't know if they're going crazy and dying or not. Hopefully not. That would be very sad. Anyway, so we've got is allocated, our precondition of it being true, now being true, because we just did this this operation. We did a malloc, and doing a malloc makes is allocated true. Okay, so and it makes it true, right? Because it makes it true because this is the malloc logic, right? At the very end, it sets is allocated to true. Okay, so now we fork, and the reason we fork is that we want to start performing operations concurrently. So even though we're sending, in theory, this would still work even if we didn't do this in a separate thread. It's probably just going to be much less likely to succeed. And the reason it still could work is because we're sending all of these things kind of like over the network, and who knows what order they're going to arrive in, and stuff can be interleaved or whatever. But this increases the odds because we're making it kind of happen in a separate process. We're making it happen, in a separate process. It's going to happen at the same time. So we're calling free. So you could kind of think of this, we're calling free, it turns out, in thread 1, but you could think of this as being our thread 2. So maybe we'll call this R1. We're basically spam calling free as much as possible. Yeah, okay, so we're calling free a bunch of times. And then also we're calling scanf a bunch of times with packed. And what is packed? Packed is pwn.p64 address. And pwn.p64 address is the address that we're trying to make our allocation go to. So we are calling this in R2 based off of the exploit. Okay. And then we are waiting. Okay. And then we're basically checking to see if we succeeded. So the first time around, we're definitely not going to succeed because we will have called malloc in order to set malloc basically to have set is allocated to true. And then we go through and execute these, which means we won't basically be able to have executed malloc again at the end, but that's fine. This is just the first loop through. And then, so basically we're trying to check to see if we succeeded. And the way we do that, the first thing we do is we printf our index. So we're all of the way through. This index is basically working on allocation 0, for instance, at the start. Or in this case, I guess allocation 1, because index is initially 1, and we increment that later on for a reason I will explain later. We're just working here on this. So we are always working on allocation 1. So we print it and we see if it returns none to us. And as we said before, let me see if I can go back up to this. It'll tell us none if is allocated is set to false. So we're assuming that is allocated is set to false because we're assuming kind of like these frees will have basically executed it at the end a bunch of times. Basically, the idea is that we will have malloc and then freed afterwards, and a bunch of frees will have happened, and that is allocated will be set to false. So that's why we're asserting that none is in result. Okay, hold on. Yeah, okay, that's fine. So that's why we assert none is in result here. But then what we do is we call malloc again, and we print f. Let's see. We malloc, we printf, and then we read in that data to see what the message returned to us. And we're basically saying, okay, what we're basically saying here is we're checking to see if we succeeded. And the way that we will have succeeded is that if we call malloc and printf and read until message, if this returns to us the address that we're trying to store here, so if we go back to this logic here, so we have this scanf, and this scanf operation is accompanied by us trying to force our allocation to a particular address. And that if that address is actually in here, we will have succeeded. Let's see. So in this situation, oh, like, okay, I understand now. So the reason that this works is that we call malloc, which will, actually, hold on, let me jump ahead to see how we finish out. So in R3, we call free 0, and then we malloc 0, or malloc 1, free 1. Three. So let me think here for a second why this matches up with our conceptual attack. So something to note is that this free will only succeed once. Even though we send free 2,000 times, it will only work in the instance where is, so well, basically, I mean, theoretically, it could work more times. Actually, no, that's not true. It could only work one time. And the reason it can only work one time is because this free operation is always happening on the same thread. And it will succeed when is allocated is true, because then it will go through and it will free and then set it to false And once we've set it to false, since all we're basically at this point in time, all we're doing is freeze and scanfs, and scanf doesn't control is allocated. It doesn't change the value of this. When is allocated is true, the free will go through and set is allocated to false, and then all future of these 2,000 attempts will fail. Or it just basically will be a no-op. It won't happen because is allocated will be is allocated will now be false, which means it won't enter here anymore. So this operation here, even though we sent it 2,000 times, will only succeed once. And this scanf, in theory, could succeed multiple times. Yeah, there's no problem with that, but we would be constantly overwriting the same thing. I'm really curious about like changing up how this control allocation works, because I think it technically will work, but I think it's maybe a little more tricky to look at than it needs to be, but maybe I'm missing something. So the way I see it is that basically hold on, let me keep looking at it. So eventually we call printf index, and we know that assuming that one of these 2,000 frees succeeds and sets is allocated equal to false, which I think must happen because it's very likely to happen. I'm almost certain it must happen. And once is allocated is set to false, now this printf is going to spit out none to us. Okay. And then we malloc. And then we printf. And this, when we do our malloc, we will get back the allocation that was freed. Is that true? Actually, hold on. So, because it depends on the thread. So this R1 is the person doing freeing, and then eventually R1 also does the malloc. So we're working on its Tcache. So that will be the same guy that got freed here. And once we call malloc, the first 8 bytes won't get modified because that's not what malloc does. But the forward pointer will still be sitting there. And then we print it and we see if we successfully corrupted that forward pointer. Yes, okay, so this makes sense. Right, okay. I was definitely getting confused there for a second. It's definitely, it takes some work to think about this. Okay, so the thing that we're not like tracking in terms of while we're stepping through this code is what Tcache can look like at all of these points. So Tcache is going to, at this point, once we do, let's say this printf, basically after, yeah, like right in here, Tcache is going to look like our freed chunk, and then that will be pointing to, aka what the first 8 bytes of that freed chunk are, will be packed. Basically the address that we're trying to make it be. So the first thing we do is we printf, and we see it says none, which makes sense because is allocated is set to be false, and when is allocated is set to false, as we talked about a long time ago at this point, it prints out none if is allocated is false. Okay, and then we call malloc, and when we call malloc, that is going to return to us that initial freed chunk, but it's also going to update tcache to be our packed address. So that's basically going to be the next thing that comes out of malloc. Okay, but those 8 bytes are still sitting in this freed chunk, even though we've updated tcache. It would be a waste of time basically to change the first 8 bytes to no longer contain the forward pointer. Might as well just keep it there as uninitialized data because that's quicker. So we actually go on to printf it. So we malloc it, which updates tcache to be now the next thing will be packed. And then we printf that freed chunk, printf freed chunk, which is actually going to spit out to us packed because that was the forward pointer. And that tells us once that is true that our sequence of events was correct, because this means at this point that we were able to see that packed is the result. That means that inside of tcache, the next thing in line is this packed address, which means malloc is going to return packed to us. Okay, so this confirms that we're good to go, so we can break out of this while true. And the reason that we need to loop this is because this is a race. It's a race, so we need to basically get the right sequence of events. We need basically this sequence of events to occur. So we're just kind of looping until this sequence of events occurs. And we're able to check that this sequence of events occurs by printfing the freed, now malloc chunk, and it returning back, basically packed back to us. At least I think that will work. It certainly sometimes works, but apparently we've already seen that this exploit sometimes fails. So maybe that check's not exactly correct, but it seems mostly correct. Okay, and then what do? We call on R3, we free. We free to R, okay, this makes sense. We free to R3 just for the sake of doing it. I think this probably keeps the cache consistent in our connection. I'm not exactly sure why we need this. I don't think we need it. But we might need it to be able to basically call controlled allocations multiple times. So basically what this is going to free, and notice how instead of on R1, so basically every single R, we have R1, R2, R3, each of them has their own tcache. So when we call free in malloc, we're operating on that person's tcache. So even though we called malloc and got our allocation here on R1, we're freeing it back to R3. So we're not actually messing up R1's tcache, which means that this tcache being packed is still true. So we basically just take that chunk we got and send it back to R3's tcache, which might make sense because, yeah, and this is why at the beginning of this we call malloc from R3, because we're going to get that guy back if we call controlled allocation again, because this is now going to be the person sitting at the top of tcache for R3. So we send this allocation back to R3. But now the next guy in line, still R1's tcache is still pointing to packed. So when we call malloc here, we are finally going to get our controlled allocation, which means basically the whole point of this function is to give us a controlled allocation to a specific address. And we have succeeded at this point. Okay, so then what do? So when we want to do an arbitrary read, we do a controlled allocation. We've just forced an allocation to be where we want it to do, as discussed over the last 1+ hours. Okay, so then what we do in order to get our arbitrary read is we have our forced allocation pointing at packed or whatever address we wanted it to be allocated to. And we call printf, and we just read until message, and then we read whatever data is there. And if we pointed this, for instance, at secret adder to do our arbitrary read, now we've just read the first 8 bytes. And the reason it's the first 8 bytes is because the second 8 bytes in this is going to be our, it's going to be nulled out because that's what malloc does, because initially there was, when it's freed, there's a key in there. And the key basically keeps track of preventing a double free from happening. And then when you call malloc, it nulls that out to say basically it's no longer freed. So that's why you can only get 8 bytes. But you can just perform this again because the secret doesn't change. And we've already seen now, let's go ahead and run this. It doesn't completely, it's not 100% consistent. I guess it worked here. We saw before though that sometimes we're leaking null. So there's some quasi issue with this exploit, or maybe it's just that since we're only, who knows, I'd have to look further into it. Somehow our race isn't guaranteed to work, and I think there's potentially some ways that we could clean up the exploit to make it guaranteed to work, but maybe I'm wrong about that idea. But either way, it sometimes works. And when it sometimes works, we can get our secret, and then you just need to leak the second part of the secret, send that off, and you get your flag. And all 6 of these levels basically follow this concept, but leaking memory around in different areas. So, yeah, that's kind of the idea. And Jan kind of has already talked about in his Q&A some of the other areas, how you can start leaking them. So there's actually something that I created that might be interesting. Let me see if I can get it to work. Hold on. Let me leave this cd projects ls memscanner. Yeah, this. Okay. So I created this thing that might be interesting to you guys working on these 6 levels here for understanding basically pointers in memory. It's kind of just a very simple tool. We'll just kind of maybe print it out. Memscanner, memscan.py. It basically just goes through and finds pointers in memory regions pointing to other memory regions. So what do I mean by that? If I go into memscanner, my example here was just like bin sleep. We'll just have that run. And then we run this memscanner against this PID. It basically just takes in a PID. I guess I have to enter my password. It just goes through and finds pointers in a particular memory mapping pointing to a pointer in another memory mapping. So for instance, the binaries read-only section here has a pointer that goes to libc. So that means that if you knew where this page was and you were able to continue doing arbitrary reads inside of this, you would be able to get to libc. If you knew this, you'd be able to get to the stack. If you knew this, you'd be able to get to libc again, another way you get there. And if you knew like some stack addresses, for instance, you could get to LD or you could get to libc. The important thing for these levels, once you've got your arbitrary read working and it kind of makes sense to you, is going to be pivoting around in memory. So say you have let's say some pointer, or let's see here. Let's say you know where libc is, but you need to figure out where the challenge binary is at. Because of pi, right, it's randomized. And maybe you want to leak something in the BSS where where pi is turned on. So in level 1, pi is turned off, but let's say it's turned on, but you know where libc is. If you can find a pointer in libc that points you at the binary, so for instance, this one looks potentially promising. If I know where libc is, I can read out this address, or I guess this address. If I do an arbitrary read here, the data will be, or what the contents of the value is, will be here. Which means that if I read out this memory address, now I know this memory address. And if I know this memory address, now I've just broken pi. So these levels are going to kind of force you to pivot around in memory, is going to be kind of the general idea going forward. But I think this once you have your arbitrary read and arbitrary write mechanism, it'll take some thinking to figure out kind of how to pivot around in memory, maybe some reading and kind of understanding what's going on here. But I think the much trickier part is getting your arbitrary read to work. So once you have that, hopefully you'll find it more enjoyable pivoting around in memory, which is a very useful skill. Okay, so are there any questions? I'm going to start wrapping up office hours because I think what I've explained basically covers everything at play within these 6 levels. So yeah, are there any questions before I? Yeah. Yeah. So if you just like git clone or https github.com/ConnorNelson/memscanner is where it's at. Maybe you'll find it useful, maybe you won't. I don't know. It basically, the whole idea is I was just thinking about the idea of figuring out where a pointer in one memory region is that will bring you to a pointer in a different memory region, because that's kind of what these levels are going to be all about. So you can either just like kind of sit there and scan through memory, which is what this tool does, in order to figure out, for instance, that there's a pointer in libc that points to the binary, which basically means that if you had already leaked out the address of libc, that now if you given an arbitrary read, you could leak out the address of the binary, which kind of breaks pi in that case, or all sorts of things basically. If you have the heap, you could get to libc. If you have a pointer inside the heap, you can get an arbitrary read again. Now you can get to libc, and then you get from libc to the binary, you get to whatever. Basically, you pivot around in memory is the idea. If you're interested in this tool, maybe it'll help you, maybe it'll not help you, I don't know. You can get it from there. Okay, are there any more questions? And maybe this will make more sense once you start working on like level 2 and level 3. But I think once you've solved level 1, you're in a very good place for solving the remaining levels. There will be more tricks involved in terms of pivoting around in memory, but getting your arbitrary read primitive working is, like, in my opinion, the most tricky part of these levels here. Yeah, from there it's figuring out how to pivot around in memory. Any more questions? All right, I will take that as a no. If you do stumble into a question, feel free to ask in the help channels. If it's super specific and for some reason you can't ask it in the help channel, feel free to either email us or message me on Discord or whatever. The same policy as we've been doing this whole semester. Okay, all right. Thank you for attending my office hours, and good luck on the challenges.